Alright, so we're back. We have a little bit more of a complex molecule to talk about now. In our last video we talked about a molecule with just one stereogenic center. They're pretty simple to manipulate with a little bit of practice. It gets a little bit trickier when we have these molecules with two or more stereogenic centers. So looking at this molecule right here, we can see that we're going to pretend that this, you'll notice there's no ball at the end of this. We're going to say this is just a methyl group. So it's a hypothetical, just a carbon with three hydrogens out here. We have our red, our blue, our white, our red, and our green. So right here you'll see that we have one stereogenic center, right? Because none of these substituents are the same, and then it goes out here to this substituent. From here, all of this is a substituent of that carbon, right? And likewise, we can look at it over here, and we'll say, alright, look at this carbon. It's got a methyl group coming out, it's got a red group coming out, a blue group coming out, and then it also has a substituent. This entire section from here, all of these is a substituent of this carbon, right? So we have two stereogenic centers. An important thing to do is to, what would you say, label them. RS designations for each one. We can't do that right here because what is the the rules, what's the priorities? Does red or green come first in priorities? So I mean, we can't do it with these. We'd have to designate them, one bromine, one chlorine, one carbon, this and that, and we won't do that for all these colors. A little bit too confusing. So looking here though, let's pretend we did do that. What can we say about this? What kind of, what would you say, developments can occur to it? So it could have, for example, an identical copy of itself, right? It could also have an enantiomer, which is the mirror image of it, as we said before. So if we were to pull out our mirror again and look into the mirror, that what you see in the mirror makes sense. That's the mirror image of our molecule. So that's what we're supposed to picture when we draw it with, you may have seen in prior videos with our little line, we're supposed to be looking at it kind of like that way of a mirror, but from an angle we get a better view of that mirror image. But putting that away right now, so we have our identical possibility, our enantiomer possibility, and we have that, the diastereomers. So a lot of people seem to be confused when they first learn about the diastereomers. It's kind of a, what would you say, not as something as straightforward. I mean, something that is identical, I mean, you don't need to do much thinking as to what that means. It's pretty common sense. If they're identical, they're identical. The mirror image is another one, although a little bit more tricky than identical. The mirror image is still pretty straightforward because all of us know what a mirror is. Diastereomers is a little bit different. It has to do, I guess, with, I guess you could look at it a few different ways, but one simple way to think about it in physical terms is that at least two of our substituents somewhere on a given stereogenic center are going to be switched. And when that happens, when that switch happens, you remember in prior videos we talked about rotating the molecule, and we talked about something like this, actual physical rotation of it. Well, this time we're going to talk about what we said was a no-no, where we rip off this blue, rip off this red, and actually flip their spots. So we didn't rotate the whole molecule, we just rotated two given substituents on the stereogenic center. And by doing this, we actually invert it. So for example, say this was a R stereogenic center. Once we did that little flip, it's going to become an S. If it was an S, once we did that little flip, it's going to become an R. So that's kind of a ramification of what happens. An important thing to keep in mind, you'll notice that this bond connecting these two carbons here, it's a single bond. So what can we do with single bonds? Do they rotate or don't they rotate? hopefully you remember that double bonds do not rotate. We can't, break them and then remake them easily just to, get that rotation. But with a single bond, we can. Let's see if I can get this here. Tricky. Alright, so we can get them to rotate. Notice that the blue is staying down, but the side in my hand can rotate freely. And by doing that, we aren't necessarily making, any type of severe change to the molecule. We aren't making constitutional isomers by rotating this single bond, and we aren't making, necessarily diastereomers out of a molecule just from rotating it, and we aren't making any enantiomers out of it. We aren't changing it at all. We're just rotating a single bond, which is completely permissible and allowed to do. When that comes in handy is when you have your question on your exam that's going to say, are these molecules identical? Are they mirror images? Are they diastereomers? So very rarely are you going to have such a straightforward, question where they're going to be exactly oriented, where you can literally just look at one and then a second see that they superimpose. They're going to be manipulated and twisted in such a way that you're going to have to do that rotation of that single bond to orient them to find your answer. So let's look at a sister molecule here. So we have this one right there. You'll notice that they have the same number of given substituents. We have 2 reds on this one, 2 reds on this one. We have our 2 methyl groups. We have a green. We have a green back there, and we have a white and a white. So they are, what would you say, at least isomers in some sense. They have the same, elements making them up. But let's go a little deeper. Can we make mirror images out of them? Are they superimposable? Are they identical? So let's start with our simplest one usually and say if they're identical. One way to do that, you could either determine the RS designations of them and see if they're the same, or you can actually picture them in your head. Keep in mind, you won't have your models during an exam, but if you can start to practice and exercise your brain in the way of doing this, then it will help you greatly. So let's see. Let's first line up our methyls there. So we're going to want to turn this like that, right? So like this, and we see that our methyls are lined up, but our blue and our red aren't lined up correctly, right? So already we have a big problem, and we've already found that they aren't going to be superimposable, because no way that we rotate these are we going to get those 2 methyls to line up with these blues. For example, the blues are lined up now, but now this methyl is lined up with a red. If we line up our reds together, so our reds are lined up now, we have the blue with the methyl. So no matter how we manipulate this, we aren't going to get them to be identical. So we can cross that off of our list. We now have it down to mirror images or diastereomers. So can we make a mirror image out of these 2 molecules? Well, that's where we have to start doing our rotation. Right now as they sit, are they mirror images? You'll say, alright, those 2 match, these 2 blues match, these 2 reds in the back match, these. So if you were to chop it off right there and chop this one off right there, just this section in between my hand, those are mirror images. But that's not the end of the molecule. We have to consider the whole molecule, right? So we have to look at those back ends as well. As they sit right now, are they mirror images? So you see a white up there and a blue up there. No, they aren't going to be mirror images. So this is where, it's not safe for you to mark that on your test right now. We need to try and rotate that single bond. If it was a double bond, we'd have our answer, and we say, well, we can't rotate it, so we can probably mark that off too. But it's a single bond, so let's start rotating. So let's rotate that way. Notice that our front orientation still stayed the same. Our front is still mirror images, but we rotated the back with that single bond. And let's see, so we got a red over here and a green over here, a white up top, up, well, looks like we have a green in the back and a red over there. So we're close, but no cigar. We still don't have mirror images, right? So we can see, just looking from there to there, that they aren't mirror images. Bringing back our mirror again, we can give ourselves a hint as to what we want to see. Notice how the green is lined up with the green, the blue is lined up with the blue, the whites with the white, and the two reds are lined up with the two reds, right? So in reality though, what we have, we're working with this, and they aren't lined up perfectly. So we could try and rotate it again. So let's try and do that, see if we have any luck. Our greens now are lined up. As you'll see, our blues, like we said before, nothing changed under the part under my hand. These two areas are still the same. We have a green down here now, a green down here now, but white and our red, so they still aren't mirror images. So we pretty much rotated it every which way we can. This is our last rotation we can do of it. So just as we've seen, everything in the same mirror images, the part under my hand, but looking at the rest of it, while we have our reds nicely lined up to be mirror images, we see that we have a green there with a white there, and a green up there with a white over there. So yeah, so still they are not mirror images. So I think we could safely say that we have some diastereomers in our presence right here. And the way you can test that is again by doing their RS designations and comparing them. But another way to do it real quickly is to pick out one of the molecules. So let's pick out this one underneath my hand. We picked out this one. This is the one we're going to manipulate for our little test right here to see if it's a diastereomer or not. So our test is going to be, we're going to pick out just two of the substituents, and we're going to flip them. Alright, we're not going to rotate the overall molecule. We're not going to do anything like that. We're not going to rotate this, this single bond. We're just going to pick out two substituents, consider them isolated, and consider them for our purposes ripped off and put in each other's spot. So let's say we're going to rip off this, if I can get it, rip off that green, and remember the white was down below. We're going to rip off, it's kind of hard to do with one hand. Alright, yeah, I must have glued them on there earlier. So we ripped off our two substituents. Remember, our white was originally down below, and our green was originally up top. We want to test them to see if we can make diastereomers, a little test for it. So as you could see, as they were before, they aren't mirror images, right? The white's on top, the green's on top. So here's our test. We said we're going to rip off two and only two substituents, but we're going to flip them. So we've ripped off the green and we've ripped off the white. We're going to put the white one up here, and we're going to put the green one down there. So when we do that, what do we have? We've flipped two of them, and let's zoom out a little bit, and suddenly it looks like we have mirror images, right? So our blues are lined up, our methyls are lined up, our whites are lined up top, and our greens in the rear of each one are lined up, and on the back side all of our reds are lined up. We've made a mirror image by flipping just two of the substituents on a given stereogenic center. If I would have flipped two more, probably we would end up with something similar to what we started with. So you want to remember to just flip two of them, just one time. Don't keep flipping around in that way, and just use this as a test for a diastereomer. So through the merits of what we just found, we could say that our original two molecules, when our white was down there and our green was up here, these two separate molecules are diastereomers of each other. And again, spend 5 minutes to do it with your own model sets, and hopefully come test day you'll be able to do this in your head fairly quickly.